Hello, everyone.
Good morning. How you doing?
Not too bad. We were a little bit ahead, and my dad was having surgery the other day, so I canceled class to go be with him. Sadly, I got there and he was already done, so it was a little bit of a waste. But anyways,
Is he doing all right?
yeah, he had a pacemaker put in. He's 76, 77 years old, and started having some problems. They put a pacemaker in. We were worried about. He was scared a little bit about it, which is he's very seldom scared of anything. So I wanted to be there to support him, but it was really a minor thing, evidently, because they were in and out in like 10 minutes.
I'm glad everything went well.
Thank you. Yeah, I am too. Uh, so we're actually, like I said, a good ways ahead as far as what we need to cover. I told you we already have the practice tests up for chapters 10, 11, and 36. I've done basically 36, and between what I did in class and the I think now I have six special relativity videos, just called special relativity 001, special relativity 002, on up to 006. They're all posted on my YouTube channel as well. I think between those examples and the examples that you see from previous semesters as well as from this course, you've got more than enough examples to make sense of chapter 36. Uh, Chapters 10 and 11 is what we're doing next, and today I'll do a good fraction of chapter 10, and then we'll go on to chapter 11. And after that, we'll go to elementary particles and maybe even nuclear physics, which would be kind of cool. So, anybody have any questions before we get started?
I just have some questions of the homework last night, but I can ask them after class.
Okay, yeah, that'll be fine. I'll get you to share your screen when we do that, and anybody that wants to stick around and ask about it, that's cool too.
Yeah, I got a homework question too.
Okay, no problem. All right, so I thought I'd start off by discussing rotational motion, just in terms of sort of everyday life. Specifically, I'm going to use an example that I was just recently playing with, which is my zero turn lawn tractor. I've got a 50-inch zero turn Toro lawn tractor because I really love a pretty lawn, so I try to get sort of decent things to keep it nice and pretty. And then one day I was bragging to my students about how great it looked, and I pulled up Google Earth and showed them my house, and evidently Google Earth took the time to take a photo of my house during the winter when all my Bermuda had turned brown. So it's literally this beautiful neighborhood with all green lawns, and mine was brown. I was like, darn it. So I'm waiting for them to do another flyby and make my yard look better. My daughter reported the other day that the Google Earth finally got my yard looking better, but I'm not. I haven't checked it myself, so she might just been blowing smoke to make me feel better. But anyways, I was looking at that lawnmower the other day, and it told me the velocity of the tip of the blades, which is very much related to a rotational problem in physics, which is what we're doing today. And in fact, I think it was 203 miles per hour was the actual velocity of my blade tips. I'm looking in the wrong one now, so let's look in this one. Yeah, my blade tip travels at 18,330 feet per minute, or 208 miles per hour. So that's pretty darn fast. And those blades are heavy. And in fact, they're 17.5 inches long. So we can actually use that to find out what the rotational rate is, which is what we're talking about in in this chapter 10. So what we've done is chapters 1 through 9, we covered mechanics. We covered dynamics, which is the what makes things accelerate, by using vectors and F equals ma and vector addition laws and stuff like that, how to add vectors. We also did kinematics, which was chapters 1 and 2, where you're doing x equals 1/2 ac squared. So in other words, what kind of distance is traveled, what kind of a change in velocity do you have for a given acceleration. And then, like I said, the dynamics part is how do I make that accelerate? What are the forces that are required? And all of those are really dealing with point objects. So we're all pretending the objects that we're dealing with, even though they're not necessarily, like when you're talking about a car, it's clearly not a point object. But now we're going to loosen that up and actually allow it to be something with some physical size. And in order to do that, we've got to start with rotational motion. Because, for instance, if you take the x equals 1/2 ac squared plus v0t equation, and you take the A is equal to V minus VF, or excuse me, you take the VF squared minus VO squared equals 2AX equation, and you can combine those, and you combine it also with the Y motion equation, and you can get an equation for Y and X that doesn't have the time. So if you make a plot of Y versus X for a projectile, you'll end up getting a parabola, which is what we expect, right? We expect objects thrown to follow parabolic paths. That's sort of what we've been learning about in projectile motion. But if I throw this pin, what part actually follows a parabolic path? Well, it's not the tip, because when I throw this pin, it's going to be doing this thing going through space, right? It's actually the center of mass of this object. And the way you can treat this object, if you wanted to physically and actually be able to make some predictions about it, is you can treat the center of mass as a point object, and you work out the F equals ma and the x equals 1/2 at squared plus b0t plus x0, and that'll get you the parabola. But then you say, okay, well, let's let the angle, treating the center of mass as a vertex, let's let the angle between the positive x-axis and a point directly above somewhere along the object, let's let that angle be theta. And then we can not only know how high or how far away or how fast is moving the center of mass, we can even tell, well, how fast is the tip of the pin moving? What about the other tip of the pin? How fast is it rotating? What's its orientation just before it hits the ground? Is it like this? Is it like this? So it's actually going to stab in? What? All that stuff can now be worked out. And that is really no longer dealing with point objects. That's actually dealing with physical objects. So we can introduce things like torque and stuff like that, giving us a more realistic idea of motion. So it's motion of solid bodies, and the way we normally treat them is we assume that they're rigid. So it's rigid body motion. And what we mean by that is if I take the center of mass here, and that has an x and y coordinate, and then I go over here and find any other point in the mass, and I find an xy coordinate for that, and then I use the distance formula to find the distance between those two. At any point in time later, that distance will be exactly the same. That's the definition of a rigid body, is it doesn't stretch or contract, okay? So then when you study rigid body, you just really treat it as a center of mass plus what it's doing rotation-wise. So that's where we're going with chapter 10 and 11. We won't get much into actually solving those big problems because there's so much work for so little reward. But if you ever had to physically do it, then obviously it's worthwhile for whatever project you're working on. So let us start with rotational motion. And the fundamental idea behind rotational motion is something we all know from trigonometry. It was how we define the radian angle. So there was a neat little formula we used for arc length, and we found that in trigonometry, S, a little bit of arc length, S, was equal to R times theta. And what we meant by that was if you had a circle of radius R, okay, it's not a horrible circle, it's not great, but it's not horrible, and it actually fanned out an angle theta, say, then this distance S is the arc length, and that's given by R times theta, where theta is measured in radians. Okay, so given that our formula for the circumference of a circle, this is not coming very neat. Let's do it this way. That's better. Given that our formula for the radius of a circle, or for the circumference of a circle, C is equal to 2 pi times R, which could also be written as R times 2 pi, then you might realize that 360 degrees is equal to 2 pi radians. So remember, our conversion factors that we learned about in chapter 1 say, hey, if you have two quantities that are equal to each other, you can make a ratio of them. So you can write 360 degrees over 2 pi radians, or you can write 2 pi radians over 360 degrees, and both of those are actually equal to 1. Okay, so that means you can multiply any number you have by this quantity, and you're not going to change its value. Now, obviously, if I wanted to choose, if I wanted to multiply by a very specific one, I could use it to cancel out the units that I have and to get the units that I wish. So, for instance, you might say, well, what is, for instance, 1 radian? Well, 1 radian can be multiplied by, so I'll say 1 radian multiplied by 1, and I'll write this over 1 just to remind myself that that is in fact a numerator. Now I wish to get rid of radians, so I'm gonna have to put radians in the bottom to get rid of it, which means I need to use that version. And in fact, I can reduce it. Instead of doing 2 pi and 360, I can do 180 and pi, and that'll be fine as well. So I'll write pi radians, and then I write 180 degrees, and now I carry out the math, and sure enough, you take 1 and multiply it by 180, and then you take that answer and divide it by pi, and when I do that, I get 57, I thought it was 54 for some reason, 57.11 degrees.
I got a slightly different one. I got 57.29, or I guess 0.3.
I only carried my because I was using a dumb calculator, I did 3.14159, so that might be the reason. Let me see, 180 divided by, let's see what happens when I actually use the pi button. It gets me very excited to use the pi button. 57.29, yes, you're exactly right. I wonder, I probably made a typo. That's probably what happened. Thank you for catching that. That's excellent. That's exactly what I need. I've had 2 days in a row my students doing this. This is awesome. So the answer turns out to be 57.30, I guess would be, because it's 295 radians, degrees equals 1 radian. So now we know, that a radian is about 57.3 degrees. That's a pretty big swath. It's almost 60 degrees, of course. You can also say, well, what about 90 degrees? Well, if I said 90 degrees, I could then multiply that by something with degrees in the bottom to get rid of it. So I'm going to take again, you could use the 360, but why use such big numbers? And then that'll be pi radians. So I think you all know what's going to happen here. 90 divided by 180 is 1/2. So this would be pi over 2 radians, which is what you probably already knew anyways. You can do that for 30, you can do it for 60, so on and so forth. But the big thing is you ultimately get this S, this arc length, which is like our X that we used before. And remember, we had this wonderful equation that you can get in terms of X. We could say, for instance, V is dx dt, and then we could say A is dv dt, like that. Well, guess what? We can do that same sort of thing here. We can say that omega, which is the angular velocity, is d theta over dt, because theta is playing the role of x. Theta plays the role of x. I always want to spell that R-O-L-L for some reason. I don't know why. I think I'm special. Okay. And then alpha, the angular acceleration, is actually equal to d omega over dt. And of course, this is d2x over dt squared. So this is d2 theta over dt squared. Both equivalent. Okay. Now, because of that, we can say alpha is equal to a constant. Let's pretend for a second that alpha, this would be the radians per second every second. So how much does my radian per second speed increase per second? If I set that equal to a constant, not unlike letting A equal 9.8 meters per second, then I have alpha equals d omega over dt, which gives me alpha times dt equals d omega over dt times dt. Now I can integrate both sides, and I'm going to integrate from t 0 equals 0 to t. And this side, I'll integrate from omega 0 to omega of t. So that's omega of t, that's omega sub 0. I'm sorry I wrote it so small. Let me bring it up here and leave it out of focus so you can see it a little bit better. There you go. So that's alpha integrated from t0 equals 0 to t, and alpha is being a constant, of course, and then d omega dt times dt is being integrated from omega equals omega 0 to omega of t. Okay, so that's our goal. Now I'll focus it back. Yeah, that looks pretty good. Now on the left-hand side, I end up getting alpha t is equal to omega of t minus omega 0. So I have the expression omega of t is equal to omega 0 plus alpha t. Well, that looks exactly like the equation we had, which said v of t is equal to v0 plus at. So that looks just like our kinematic equation we had before for linear motion, doesn't it? Well, we can do the same thing now. We can say, well, wait a second, omega of t is equal to d theta over dt. So I can say omega of t is equal to omega 0 plus alpha t is equal to d theta over dt. Well, that gives me integral omega 0 plus alpha t dt, and I'm going to integrate from t0 equals 0 to t of the integral of d theta over dt times dt. And I'm going to integrate this, of course, from theta 0 to theta of t. So I'm doing the same sort of process we did before with kinematics, only now I'm doing them with kinematics in rotational motion, which looks just like this. So now on this side, I end up getting 1/2 alpha t squared plus omega 0 times t is equal to theta of t minus theta 0, or theta of t is equal to 1/2 alpha t squared plus omega 0 t plus theta 0, which is another wonderful kinematic equation, but it looks exactly like x is equal to 1/2 a t squared plus v0 t plus x0. And in fact, that is the linear analog to the rotational equation. Now, we also were able to use this equation right here. If you solve that for t, you can plug that back in here. So t would actually equal to omega minus omega 0 over alpha. And I plug that into equation 2. Then I get theta, which I'm going to stop writing the theta of t. I'll just write theta like I did the x before. Theta is now equal to 1/2 alpha times omega minus omega 0 alpha squared plus omega 0 times omega minus omega 0 over alpha plus theta 0. Well, that again gives me theta is equal to, now one of these alphas will cancel out in the bottom, so I'll get over 2a, I'll get omega squared minus 2 omega 0 plus omega 0 squared plus omega 0 minus omega 0 squared over alpha, and then of course plus theta zeros on the end. I ran out of space there. Let me again show you what I wrote, since I ran out of space thinking I could fit it in that area. So by squaring the omega minus omega 0, I got omega squared minus 2 omega 0 plus omega squared. All of that's over, that's supposed to be an alpha, I wrote an A. Okay. All of that's over 2 times alpha because the 1/2 was already there. Now when I carry out this omega, distribute it through there, I get omega 0 minus omega 0 squared, all of that over alpha, which you can imagine I'm going to get a common denominator. And then I'm adding theta 0 to it. So now I'm going to get, and I'll start further over here so I make sure I have a little bit more room. I'm going to get theta is equal to omega squared minus 2 omega 0 plus omega 0 squared. Now I'm going to add to that plus 2 omega 0, because I got to multiply this by 2. Oops. Okay. Because I got to multiply this by 2 over 2, that's going to become 2 omega minus 2 omega 0 squared. So minus 2 omega 0 squared. All of that will be over 2 alpha. And then I'll say plus theta 0, because that was the end there. And you can see what happens in this case. These 2 cancels out that 1. These 2 cancel out completely, the 2 omega 0 and plus 2 omega 0. So I end up getting just omega squared minus omega 0 squared. So I can ultimately write omega squared is equal to omega 0 squared plus 2 alpha times theta minus theta 0, which I think you can recognize as just like our VF squared equals VO squared plus 2AX minus X0. So the neat thing is with kinematics in rotational motion, all the problems are exactly the same as we did with kinematics before, except now when you talk about displacement, you're not talking about X in meters, you're talking about theta in radians preferably. If you use radians, these equations will always work. In some cases, these equations will work with other things other than radians. So sometimes when you're learning to, get the training wheels off, then you just got to stick to radians for a good period of time. But those are all the equations, and that means we really don't have to cover the kinematics of rotation that much. You should do some problems to get used to it and to get used to what the units are. So remember the units, of course, for theta, the unit should be radians. That always works, but sometimes you might want to use something else and it may or may not work. The units for omega is radians per second. Again, that always works, but sometimes you might want to use something different and it may or may not work. And then finally, the omega for alpha is equal to radians per second, just like it was meters per second before. So now that we have all that, we have all our kinematic equations, we've got really neat things. And you might even realize that, wait a second, since S is equal to R times theta, you might call that distance along a arc X, in which case X would equal R times theta. Then dx dt would equal, if R is a constant, R d theta dt. And lo and behold, you have a new expression, V equals R omega. That's another important equation that relates the linear motion V to the angular motion omega. Now you can also use that and say, well, V is equal to R times omega, and A is equal to dV dt, but that's equal to R d omega over dt. So you get, in this case, A is equal to R times alpha. And that's really the equations we need, okay? So if you look at something spinning like this thing, okay, every part is spinning at a same angular speed omega. Each, like if you found that the pin covers an angle of, let's say, 45 degrees in 1 second, every part of the pin is covering an angle of 45 degrees in 1 second. So this omega is a constant for a rigid body, right? But the velocity of the tip is quite a bit larger than the velocity of, say, here, because this is only half the distance out. That's what that is showing. It's showing that the velocity is proportional to the theta, which is going to, or to the omega, which is going to be the same for all the points. But at a given distance away, you have to multiply it by that distance, and that gives you the velocity in meters per second. This is not unlike if you've ever hydroslided, scurfed, or water skied behind a boat. When the boat takes an actual turn, if you just follow the boat, you're going to go the same velocity as the boat. But if you sling out to the outside of the boat, get the rope extended where you're actually a 90-degree angle from the back of the boat or from the side of the boat, then the boat is here and you're doing this. Basically, if the boat is making a 100-meter radius turn and your rope is another 10 meters, then you're making a 110 radius turn. So instead of 30 miles per hour the boat might be going, you're actually going to get a factor of 10 over 100 over 110 times faster. So you can actually go a lot greater speed than the 30 miles per hour the boat's going. You might even, if you're taking a radius that's twice as big, you can go 60 miles per hour while the boat only does 30 miles per hour. And that again is because this V equals R times omega. Now this, by the way, is what we call tangential velocity. And this we call tangential acceleration. Okay, so that's parallel to the path you're traveling basically. That's what tangential means. These are the angulars. And then, of course, there's another one for velocity perpendicular. And there's another one for acceleration perpendicular, which if it's going in a circle, it's just going to be v squared over r. Okay, so a parallel is another way of writing this a, and that's equal to r times alpha. So it's important that you keep these in mind. You could have a velocity that's just perpendicular to the radial arm, in which case you're doing all tangential velocity. But if you actually force yourself to make velocity inward or outward, then you're going to have to use this guy, which is quite a bit different. It's basically, when I did this, I treated R as if it were a constant. If I'm doing this, then R is not a constant. And that implies V is equal to d by dt of R times theta. Now, when I do that, notice I get V is equal to d by dt of R times theta. Using your quotient or your product rule, you see it's dr dt times theta plus r times d theta dt, which is equal to, of course, r dot theta plus r theta dot. Dot is just another representation for a time derivative. And this is your V tangential, which is the same thing there. And this is your V perpendicular. Okay, so if you really want to get precise and discover all the possible velocities you can have, they're not always going to be perpendicular to the radial line. So you're going to have a component of velocity that might be perpendicular to that, and therefore parallel or anti-parallel to the radial line, and that will be given by r dot times theta. And of course, the tangential one will be r theta dot, which is the V equals r omega equation. Okay, so that's sort of all the big deals to think about kinematics. So let's imagine this. My lawnmower I drew an E instead of that W. My lawnmower has a blade tip speed of 208 miles per hour. What is that speed in meters per second? That'll be part A. Part B, given that the blade length is 17½ inches, what is the angular speed? Omega in radians per second and C in revolutions per second. Okay, so there's a problem we can solve, right? So first off, I'm going to take 208 miles per hour. I think you all know how to do that by now, but I'm going to again go through my long convoluted way so that I get exactly the right result. I know that 1 mile is equal to 5,280 feet. I know that, of course, 1 foot is equal to 12 inches. I know that, and this is the hinge, the linchpin here, 1 inch is equal to 2.54 centimeters exactly. So all these conversion factors are exactly correct. That's the beauty of using this way. And then I know that, of course, 100 centimeters is equal to 1 meter. And then I also know that 1 hour is equal to 3,600 seconds. Now, when I carry out all this multiplication, and then carry out all this division, or multiplication of the denominators, then I divide the final result. This is what I get. I'm going to say 528, or excuse me, I'm going to say 208 times 5280 times 2.54, or excuse me, times 12 times 2.54 times 1 times 1. And then I'm going to take 1 times 1 times, again, you can put this over hours if you wanted, times 1 again, times 100 times 3,600. That gives me 360 times 10 to the third in the bottom. And then up here, this gives me 33.47436 times 10 to the 6 meters. So now I just have to divide the top one by the bottom one, and I get that 208 miles per hour is equal to 92.98, carrying one extra figure, meters per second. Okay, so that's pretty darn fast. So that's part A. We've got that answer already. Now, given that the blade length is 17½ inches, then remember that's the blade length. That's from left end to right end. So the radius is really half of that. So for part B, diameter is equal to 17.5 inches, which implies the radius is in fact, that would be 8.5 would be half of 17, and then 0.25 would be half of 5. So that'd be 8.75. inches is the radius. Because if I double that, I get 16. I double that, I get 1.5. That'd be 17.5. So that works out great. So now I'm going to say times 1 inch is 2.54 centimeters. And then I'll say 100 centimeters is equal to 1 meter. So in meters, this should give me 8.75 times 2.54. And then I divide that by 100 because 1 times 100 is just 100. So I divide it by 100. And I get 0.22225. Okay, again, I'm carrying one extra digit here, just like I did before. So that gives me the actual radius. Now all I have to do is say, well, V is equal to R times omega. So omega is equal to V over R. So when I take the velocity, which is 92.98 meters per second, and divide that by 0.2223 meters, then I just get what turns out to be radians per second. Notice it's no units. No units means radians, basically. So I'm going to take this 92.98 and I'm going to divide it by the 0.2223. And in that case, I get 418.4. radians per second. So by default, that's the actual unit that comes out when you use everything in meters. So now I know that omega is equal to 418.4 radians per second, and I've carried an extra digit. And that's actually part B, because part B is where they wanted radians per second. So there's my B answer. Now I also want to know it in revolutions per second. So part C, 1 revolution just means 1 round around the track, which equals 2 pi radians. So that means omega is equal to 418.4 radians per second. Now I know that I want to get rid of radians, so I have to put 2 pi radians down here in the bottom and then put 1 revolution up here on top. So I get omega in this case is equal to that number divided by 2 pi. And I get 66.59. And that's revolutions per second. If I wanted revolutions per minute, I'm going to go ahead and add that. Then I basically multiply that by 60. And that would give me 3.995 times 10 to the third. That would be 3,995 revolutions per minute. That's part C. Now I do revolutions per minute because that's really what a tachometer is. So if you look at a car engine, for instance, when it says RPMs, that literally means revolutions per minute. So that's just a typical problem. So it appears that the spindle that a belt of my lawnmower is attached to, and that the other end of that spindle is attached to the center of the blade of my lawnmower, then that spindle must be turning at a rate of 418.4 radians per second, or in fact 3,995 revolutions per minute, which is pretty fast. Of course, 66.59 revolutions per second is pretty amazing by itself. But that's really what it's supposed to be doing. Obviously, if my engine gets bogged down because of back force due to the cutting of the grass or something like that, then it's not going to go that fast. But that's the advertised velocity. You can see, of course, since I ended up multiplying or since I ended up dividing by r, if this r were in fact smaller, so if you wanted to know, for instance, how fast the middle of the blade's going, and I mean the middle, not the center, but the middle halfway between the center and the edge, then the velocity, which is r times omega, the omega is still going to be 418.4 radians per second, but now instead of the radius being 8.75, it's going to be 4.325 times that 400. So you'd end up getting, instead of 208 miles per hour or 92.98 meters per second, you're going to get 104 miles per hour, or 49.49 meters per second, something like that. Okay, actually it'd be 46.49. That's what it is. 46.49 meters per second would be what the center is. So that's the big thing, is to realize V is proportional to R. So when you ride a merry-go-round, for instance, you know, the carousels that they have, like with horses and chairs and bulls and all sorts of stuff. Well, the farther you are out, in other words, the closer you are to the outside edge of the carousel, the faster you're going. And that's why people generally like the outermost edge, especially if you're, you know, let's say a hypothetical overweight physics and astronomy instructor who happens to be at Busch Gardens sweating his tail off. You're more likely to find him out riding the carousel on the outer edge just to get that extra breeze, because V is proportional to R. Obviously, you're also losing some of that breeze to all the other bodies if you're on the inside. So there's a lot of reasons. Similarly, when you try to take a very fast, a small radius turn, then that actually causes problems with your acceleration, because remember, A is equal to V squared over R. But anyways, that gives you a little bit of idea of what we can expect. If I wanted to ask you something like, I turn my lawnmower motor off, engine off, and the deceleration of the blade is negative 20 radians per second. So let's say this is number 2. Let's say alpha is equal to negative 20 radians per second every second. And the initial speed, omega 0, is in fact 418.4 radians per second. I might want to say, well, how long does it take for omega to be equal to 0? And I might also want to know theta equals question mark. So in other words, how many rotations or radians did it actually turn through in slowing down? Well, if I wanted the time, then I need an equation that relates time, alpha, and omega. So that immediately makes me think of the equation omega is equal to omega 0 plus alpha t. So now I can go ahead and say t is equal to omega minus omega 0 over alpha. Well, omega, the final one, is actually 0 minus a negative 20. Whoa, not that one. Minus a negative, minus a positive 92.28, I think it was. 92.98, sorry about that. 98 radians per second, again, carrying that extra digit, over negative 20 radians per second. And that's going to give me an actual, notice the radians per second cancels out with the radians per second, but the per second in the denominator becomes a second in the top. So I do 92.98 92.98 divided by 20. And of course, those are both negative, so you end up getting a positive. The time is 4.649 seconds, carrying one extra digit again. So t to slow down is this. So that's the time required to slow down. Straightforward, right? No questions on that? Now, we can also find theta, and the ways we can find theta are we can use theta equals 1/2 alpha t squared plus omega 0 t plus theta 0. And of course, theta 0, we're just going to call 0. That works just fine. So we'll say theta is equal to 1/2 times negative 20. I'll leave off the unit this time, times, in this case, we're actually using the time, 4.649. So this isn't the best way necessarily to solve the problem, because I'm using something I calculated. And if I made a mistake here, then my part B answer is going to be wrong as well. And if the instructor is not paying that much attention, you might not get any credit for this. Whereas the only thing you did wrong was make a mistake in part A. So they're actually grading you twice that way. So that's not too good. But I'll say plus the original omega, which was 92.98 radians per second times 4.649 radians per second again, plus 0. So theta ultimately is equal to, I'm going to say 20 times 0.5 times 4.649 times 4.649. And that term, of course, is negative. So I get negative 216.132. And that turns out to be radians. Plus now 92.98 times 4.649 is 432.1246. Again, carrying way too many digits. In this case, I carried way too many. And that's radians as well. So I'll add these. And I'll get 215.992. So I'm going to call that 216.0 radians. So that's the angle it turned through. Theta is equal to 216.0 radians. Remember, we found out that a radian was roughly, what, 57 degrees? And since a radian is roughly 57 degrees, 57.11, I think, 57.30, you can see that that would probably go into this close to 4 times. But we can also just convert it and realize that pi radians is equal to, actually, I should say 2 pi radians is equal to 1 revolution. So if I divide that by 2 pi, I can see it's 34.38 revolutions. So the answer for this part is 216.0 radians are 34 revolutions. So when I turn the lawnmower off, it's going to turn an additional 34.3 turns. Obviously, that's enough to still nip off a toe or something like that if you're being not very cautious. So do be careful. But and the 20 radians per second, I think actually is a little bit slow on the revolution side, because I know my lawnmower spins for probably no more than 5 to 10 seconds at most, and I really think 5 is the closer figure. So if I really wanted to figure out that, I would really say, okay, well, I'm going to say the time is 5 seconds, and then I'd compute that the acceleration would be 92.9 divided by 5. 5 goes into 45 9 times. It goes into 90, therefore 18 times. It goes into that 18.5. Well, that's weird. Oh, I did say 5 seconds. Okay, that's good. So it's less than 5 seconds. That's about right. So evidently I made up that number off the top of my head that came out fairly close to what I actually think my acceleration of my blade is. So any questions on that one? So that's how you use the kinematics. Now, this is no different than the other kinematic stuff we've used. You can do stuff like calculate how many radians a second hand has to go through before it completes a minute. How many radians must a second hand go through before it completes an hour? How many radians can a second hand, or let's say a minute hand, go through before it completes a minute? how about before it completes a second, or excuse me, an hour? Or how about how many radians it goes through before it completes 12 hours? All those are neat little conversion things that are typically done when you first learn about radians. Again, that's not necessarily what we're going for. We assume you already know that. So what we have, just to recap, we found that V should equal R dot times theta, which is V perpendicular. And this, of course, is in the R hat direction, plus, let's say, R times omega, and this is in the theta hat direction. And this is V tangential, which also is V parallel. And similarly, we found that A is equal to V squared over R, which is A perpendicular, and that should be in the R hat direction, plus R times d omega dt, which is alpha, and that's, of course, in the theta hat direction. So that's A tangent, which equals A parallel. Okay, so that's key things to remember. Those are your big results for all motion in general, but this allows not just circular motion. When you're doing circular motion, of course, you don't have this A parallel and you don't have this V tangential, but when you have elliptic motion or anything else, you're going to have to include those terms. And I think that probably explains what all this type of stuff you might need to do. You can also use this to measure things like angular frequency, which is omega. That's what it's called, omega, the angular speed, when it's revolutions, or excuse me, when it's in radians per second, or even revolutions per minute. But they also tend to talk of it as a frequency when they're saying 2 pi radians per second. That's actually a frequency. And if you want the frequency in revolutions per second, which is cycles per second, which is hertz, then you just multiply it by 2 pi. But that's more or less what we did earlier when I converted radians per second to revolutions per second by just basically multiplying it by, or in that case, I divided it by 2 pi. But if I wanted to go the other way, I multiply it by 2 pi. So we get omega is equal to 2 pi times the frequency. Frequency, of course, is 1 over the period. This is frequency. And that's measured in hertz or cycles per second, and the period's measured like in seconds or minutes, so on and so forth. So those are some other quantities you'll use. Omega is equal to 2 pi f. So you might, if you're talking about circular motion, you're really saying how many cycles, which this would be 1 cycle, does this complete every second? That's what the frequency is. So you can see frequency is cycles per second. And in fact, old manuals will say CPS as opposed to hertz. So you'll find that on occasion. And remember, a cycle is really just the same thing as 1 revolution. So when you're doing revolutions per second, you're actually doing frequency as well. So that's another parameter that might come in handy. We have all those equations of kinematics. So basically, we've done up through section 10.3 now, 11, 12, 15. Next thing I need to do is now talk about the dynamics. So that sort of ends the discussion of rotational kinematics. So remember, kinematics is, hey, how far do I go, or how many rotations do I make, or how much did my speed change for a given acceleration, or with a given initial velocity. That's what kinematics is about. Dynamics, on the other hand, rotational dynamics, is about how do I make those rotations. So it turns out, and you probably have thought of this, hopefully you have. I'm going to stop sharing the screen for a second. And actually, I'm going to turn back the camera to me. So you've probably thought about this before, but when you go to rotate something, let's say you're trying to ride a bike. And if you've ever ridden a kid's bike, you know how stinky that is compared to a regular bike, right? And actually, sometimes it can be quite hard because the force is so large. But the difference is that the shaft that comes out of the crank, so there's a crank, there's a spindle is what we actually call it. It's the chain wheel, the thing in the front that the chain goes around, and then it goes back to the back to another little wheel that's attached to the rear bicycle tire. Actually, it's actually the hub of the rear bicycle tire. That's another chain wheel. They're both called sprockets, if you will. The smaller one's normally in the back, the bigger one's normally in the front, unless you're doing some specialty trick bike riding, in which case you might have about the same size or even smaller in the front. But that ratio allows you for one turn of your pedals to do a certain number of turns of your bicycle wheel. Okay. Now, if that one turn is close to one turn of your pedal, then you're putting just as much force in as needs to actually rotate the tire. If you have, say, 4 turns for every 1 rotation of the tire, then you're probably going to reduce the force required by a factor of 4. So that's kind of nice. But in all that, you still have to apply a force to the pedal to actually make the object rotate. Now, do you think that force is bigger? Let's just say all you can do is put your whole weight on the pedal. So do you think that force is bigger when the pedal is really close to the axle of rotation for the sprocket? Or do you think that force is bigger, that ability to rotate is better when your foot is further away from that center of the axle? Let me draw a picture on my document just to let you better understand it. So let me draw a picture and then I'll turn the camera on my document again. Okay. Okay, so let me turn to my document cam again. So what I tried to draw here is this is the sprocket. Whoa. This right here is the front sprocket. This right here is the rear sprocket. This is on the actual hub of the bicycle tire. So the bicycle tire would be right about here like this. This would be the pole where your seat, basically your seat tube, your seat post will go into, and then there'd be a bar across here and a bar across here, and then this would be where your handlebars and forks go in. So this is the spindle, this is the chain, this is the back spindle. What I'm asking you is which has a better ability to rotate this? Let's say I'm trying really hard to go up a really steep hill, and I've got all my weight worked out so that I can put the maximum force up there and that I don't flip over or anything. Would I be able to impart a bigger rotational force if I put my foot down right here, or if the crank was, say, this long? I'm trying to do an extreme here, so it's a little bit easier to answer. Obviously, you're never going to have a crank that long because clearly that's longer than the bike would be high from the tires, so you'd end up hitting the ground every time. But imagine the scenario. Which one of these do you think is better capable of rotating the spindle and therefore that back tire? The green one or the pink one?
Probably the green one.
The green one. And that's the same thing like if you have a really tight nut that you're trying to release, you could take and put a wrench on it, and you put say this is the center of the nut, and you put the wrench right here and you go pull on it and it doesn't budge. Well, you scoot your hand out to the end of the wrench and it still doesn't budge. Well, your next step is to put a tube around that wrench and then get you even more of a lever arm and pull it. So what we're finding is this quantity, this thing, the ability to rotate, is actually called the torque. And what we just found that was torque, and the symbol we use for it will be the Greek letter tau. And what we just found is it's directly proportional to what I call the radius. And by radius, I mean the distance r between the point of application of the force and the actual center of rotation. So the center of rotation and that. Now this force could of course be at any angle too. I just drew it perpendicular just because I told you you're going to put all your weight on it. So that should be pushing vertically downward. So yeah, we found it's proportional to that because we decided that the bigger R was, the better the torque would be. Now, do you think it's more rotationally powerful if the force is big or small?
I want to say bigger.
Yeah, so we make the other conclusion that the torque is also proportional to the force. And in fact, that's right, okay? If you define, let's say, the lever arm as a vector that points from the center of rotation to the point of application of the force, this could be the lever arm vector. Okay. And then you could say, okay, well, what about if the force, instead of being straight down, what if the force were in fact at this angle? Okay. If the force is at this angle, theta, right, with respect to the, you notice I'm basically doing the equivalent of putting the vectors tail to tail. Here's the tail of the force vector. And of course, the tail of the lever arm vector is back here. But if I slide this whole thing this way, then it would be right here. So I'm actually taking the angle between tail to tail. Now, do you think it's more important to have this component be big or more important to have this component be big? The vertical component or the horizontal component?
I want to say the vertical component.
Exactly. Yeah, you want to have a 90-degree angle. So in fact, the vertical component, you can tell from trigonometry, is sine theta. So we're going to say that torque is proportional RF times the sine of the angle between them. And that immediately makes us think torque is equal to R cross F, and that's exactly what torque is. So there's a new equation. And we didn't have to put any constants of proportionality. We just defined it that way. Notice in the British or in the SI system, we would have units of newtons times meters. In the UK system, which is what America uses, we would have things like foot pounds or inch pounds. Basically, you multiply the length of the lever arm in inches times the force in pounds, and you get inch pounds. If you do it in feet, it'd be foot pounds. Those are actually torque units. But notice in the SI systems, it's the Newton meter or the meter Newton, both of which are acceptable. But notice that was also what we found to be the joule. But in this case, you keep it as the Newton meter, not the joule. Okay, they're not equivalent. In no way are they equivalent. Energy is not equivalent to torque except by the math of the units. Okay, so we now have a new equation. Torque is equal to R cross F. And we can solve really big, cool problems. Let me show you one. So we're going to do an Atwood machine again, surprisingly, right? So now let's do an Atwood machine. We're going to have an Atwood machine like so. And we're going to say that the radius here is just plain R. Okay. And we're going to suggest that the friction causes a torque. And that tau friction will just be called tau sub F. Okay. I'm going to hang from this a mass big M. And it's going to lift a mass little m up. What I'd like to know is what is the acceleration and what is the tension. Okay. So the first thing I'm going to do is draw a free body diagram for the mass M, big M. So there's big M. It has acting on it a tension that I'm going to call TL. And the reason why is because notice This thing, if you let it go, it would just fall at 9.8 meters per second per second. So in its frame of reference, it sees this rope as slowing it down, and we call that slowing down force the tension TL. Now, we know that part of that goes to rotating the pulley because the pulley has friction on it, and then the other part goes to lifting up the mass M, so lowercase m. So clearly the TL is different from the TR. That's why I had to label it. The other force acting on it, of course, is big mg. And what I'm going to do is I'm going to assume that the up is the positive direction. So I'm going to call this the positive y direction. Now I have a free body diagram for the other mass. And in fact, in this case, since I made up, down, up positive on that side, then up will be negative on this side. So in this case, I'm going to say, let's make this positive force. Let's make it a pinkish color. And let's make this positive force, which is lowercase mg. That's going to be pinkish as well. And then this force back here is TR. So that's the free body diagram for this one and this one. This one is this diagram, this one's this diagram. Now we got to do a free body diagram for the pulley. Okay, for the pulley, what we have is what I said was anything going this way was positive on this side. So rotation this way should be a positive direction. So that means this force on this side, T right, should lead to what I call a positive positive torque. And this force on this side, TL, should lead to a negative torque. And since we expect the objects rotating this way, there also happens to be a torque, tau F, acting that way. So that tells us that's also a negative. Remember, a friction force is trying to slow down the motion, basically. And since this object we're assuming is being lifted up, which is exactly the opposite of what I meant to draw. But anyway, since I've went with it now, saying this is going up is positive, this is going down is positive, and this is going down is positive, we're going to assume that everything's going this way is reality. Okay, obviously I drew it opposite. I don't know why I did that, but it's okay. We can still work out the math. So now I have some equations. The summation of the forces is equal to mass times acceleration. That's Newton's second law. And there turns out, here's a big thing here. There's an equivalent to this. And it is the summation of the torques is equal to something, not the mass. It's something called the moment of inertia, I, times alpha, the angular acceleration. So this is Newton's second law for rotation. Now, the I turns out to be a little bit complicated thing, but generally speaking, I depends not only on the mass, but also depends on how the mass is oriented, so how far away it is from the center of rotation. So I turns out to be the integral of r squared dm. R, it's equal to the summation from I equals 1 to n of m sub I r sub I squared. So in other words, you take the individual mass, if you have a collection of them that's countable, you take each mass and multiply it by the square of the distance it is away from the center of rotation, get a number, do the next one, get a number, do the next one, do another, and keep on adding those up, and then you get the moment of inertia, okay? What I'm going to do is I'm going to assume this pulley has a mass m, let's say m sub p, and let's say its moment of inertia, I, is, since it's a cylinder, it's going to be 1/2 m sub p r squared. That's a very typical thing. So in other words, when we start calculating moments of inertia, and I've got links to show you how to do that on YouTube, my YouTube videos, then you can calculate the moment of inertia for a cylinder, and you'll find it's 1/2 mr squared. So I can now use F equals ma to write a F equals ma for this and F equals ma for that. And then I can write a tau equals I alpha for this one. So let us begin. So equation 1 is going to be Newton's second law for this guy. So I'm going to say it's TL minus mg is equal to m times a. Okay. Then I can say equation 2, that's for this guy over here. This time I'm going to say little mg minus tr is equal to little ma. And assuming the rope doesn't get loose or taut or get stretched, then the acceleration of m has to be the acceleration of little m, because for every meter this one moves, this one's going to move another meter in the same amount of time. So that's why I didn't have to subscript the a. Now in equation 3, I have chosen that clockwise rotations are positive. So torques that cause clockwise rotation is going to be positive as well. So I'm going to say R, and notice R is actually perpendicular to TR. R times TR minus R times TL, and then of course minus T friction is equal to 1/2 MP R squared times alpha. So there's an alpha there, believe it or not. But that's the that's the actual nastiness of this equation, is I now have a relationship involving TL, TRA. Notice the number of unknowns are TL, TR, A, and that's it, right? So there's 3 unknowns. I've got 3 equations. That works wonderfully. How do I solve it? Well, I'm going to take equation 3, and I'm going to, also I've got alpha. That's another one. So that's 4. But I have an expression. Since the rope's not slipping, I know A is equal to R times alpha. So that'll be equation 4. So I'm going to plug 4 into 3. And that's going to give me alpha is equal to A over R. So I'm going to say R times TR minus, actually I'll say R times TR minus TL and just do it that way. Minus TF is equal to 1/2 MP R squared times, of course, alpha is equal to A over R. So I'll do like that. That gets rid of one of those R's like that. Now, if I divide through by R, then I will get TL minus, or TR, excuse me, TR minus TL is minus torque due to friction over R is equal to 1/2 MP A. And I'm going to call this equation 5. Notice it came from 3 and 4. That's really nice. Now, if I take and subtract, or let's add 1 and 2. So 1 plus 2, that's going to give me TL minus mg, and then plus mg minus tr. And then the left-hand side, the right-hand side will be m plus m times A. Well, that gives me something that's kind of nice too. I can say TL minus TR is equal to mg minus mg plus m times A, which I could also write as m minus m times g plus m times A is equal to TL minus TR. And I'm going to call this equation 6. Now, the reason why I did this might not be obvious to you, but guess what? I can now eliminate TR minus TL with that, and then I'll have nothing but things I ostensibly know except for A. So now I can plug 6 into 5. Only got 1 minute left. 6 into 5, and I'll get m minus m times g plus m times a minus tf over r is equal to 1/2 mp times a. So I can get all the MPs or all the A's on one side by pulling it over here. And if that's the case, actually, yeah, by pulling it over here. So then I will say that m minus m times g minus tau f over r is equal to 1/2 mp minus m times a, or a is equal to m minus m
We can't
minus,
see the way you're writing.
thank you, I appreciate that. M minus m, which is there, times g minus tau friction over r, all that divided by 1/2 mp minus m minus big M. All that, yeah, that works. So that's the actual acceleration. Now we've done acceleration with friction, and it's kind of, I was surprised to get this minus, so I'm concerned that maybe I've got a negative error somewhere. Let's see, was it, oh yeah, there was one. Notice this was supposed to be minus, and then the M was supposed to be, the big M was supposed to be plus, I think. So what I'm going to say is I expected pluses, so look for error. I've already hinted to you where the error was, but you can find that. Now, once you plug this back in, you can solve for TL or for TR, either by plugging it in here, that'll give you TL, plugging it in here, that'll give you TR. So that helps you. But that is now the modified Atwood machine, where we're actually taking into account not only the friction force, but we're taking into account the fact that the pulley has a mass. Again, I probably made some error in here. I'll let you guys try to correct that. But that's all you have to do. We have now gone through section 10.4 and even started doing a little bit of section 10.5. So we're pretty close to finishing. The rest of the stuff is really the nasty integral stuff that we use for center of mass, but now we're using to determine the moment of inertia. I will tell you this moment of inertia is a little different from the one that's used in engineering. In engineering, they end up having one that adds units of inches to the 4th power. So really what they're doing is dividing out the density of the material from the formula, which is R squared dm. Notice this would be kilogram meter squared. If you divide this by meters per, or excuse me, by kilograms per square meter or per cube meter, you'll get meters to the 5th. So that's sort of what's going on with them. That's what they use in engineering. You can look that up in your statics book. They'll probably have something about it. You might have something about it in your strength of materials book, as well as in your dynamics book for engineering. But I just wanted to let you know that that is a slightly different quantity. It's done with the same integral calculus, but because you do use different types of lumber, you use spruce, pine, fir, that's the SPF stuff. You use pine, southern pine, for instance, is the strongest, has the best characteristics. So you can use that. And each of those have a different density, and therefore they had to not include that. So that's why they did that weird thing. Everybody's free to go. I'm going to set this so that I can answer questions for people so they can share their screen with me. But we're done, and I will see you guys next week. Start doing your practice test. And now multiple participants can share the screen. I did not mean to do that.
Have an excellent week, Professor Younger.
You too. So someone, it wasn't, I know Lauren's got a question, but someone else had asked the question first. Who was that?
I did.
Okay, Miguel. So go for it, Miguel.
Let me get to the part that I was looking for.
I might actually find the error and post it on the written version of this. So check it out on my Google Docs. That'll be up in an hour or so. Check it out on my Google Docs to find the actual right answer.
Screen. Okay, so can you see my screen?
Mm-hmm.
So I just had like a couple questions for this kind of part of the homework.
Mm-hmm.
I was kind of confused as to like how to get this answer.
Okay.
I first I think I like tried to do it before on my calculator, and then I just kept getting like the wrong number, and like I tried looking for help online, seeing like if there was a formula for it, and I couldn't
Gotcha.
find anything. So
I
just
quickly
kinda, like,
gave you those formulas in examples in class as well as in the examples on YouTube. But
okay.
there's two ways you can look at it when you're dealing with a particle. The energy E squared is equal to P squared C squared plus M squared C to the fourth. That's one of them. They usually make this neat little right triangle thing where the hypotenuse is E and P times C is one of the legs and MC squared is the other leg. So when you're talking about total energy, that's what you're talking about. P squared C squared plus M squared C to the fourth. Take the square root of that. But there's also another version that's even easier, and that is E is equal to gamma MC squared.
C squared.
Yeah, you remember what gamma was?
It was like 1 over the square root of 1 minus V squared over C squared.
Exactly. So that's the gamma we're talking about. And that V over C is beta. So that's another thing. When they just give you something like 0.99 is the velocity, that what they're meaning is beta is 0.99, and that means velocity is 0.99 times C. So that kind of helps you. So with this problem, what you're going to do is you're going to say E is equal to gamma MC squared. If you have the gamma worked out already, if you don't, that's okay. You can just use P squared C squared plus M squared C to the fourth or whatever you want. What was the original problem? Can you scroll down on the left-hand side? This is one of the many interesting is that it's microseconds. Yeah, I did the problem like that. Those muons are not at rest. If relativistically, their lifetimes will be increased by time dilation. Okay. So what was part A? Did it give us a speed or anything in part A?
So yeah, part A was 3.1
So it's
microseconds.
70% of the speed of light. So what they're saying is in part A, I'll write this down on my notes. Part A, they're saying V is equal to 0.70 C, which implies beta is equal to 0.70. They're asking you for the observed lifetime. So tau mu sub 0 is 2.2 times 10 to the negative 6 seconds. But they're wanting to know tau sub mu, which is really the dilated time. Then part B said the muon is traveling at, if a muon is traveling at 99% of the speed of light, so there's part B. I'm just writing this down so when I take over the camera, I'll know what values we're using. V is equal to 0.999 C, which means beta is equal to 0.999. How long will it take to decay in the observer's rest frame? So again, they're asking you for T mu equals question mark, and then part C, which is the part you were doing, right? What is the total energy? Okay, so gotcha. So doing that, you can actually compute this. So can I borrow the camera now? I borrow the screen now.
Yeah, let me just stop sharing.
They also said the mass of the muon was 106 MeV per C squared. Is that right?
Yes.
Okay, that's a weird unit, but I'll make some sense of it in a second. So let me do my document camera. So what we have here in the first part, you were able to solve. The second part, you were able to solve. You got the right answer. But in part C,
it's out of focus. By the way.
Sorry. Yeah, boy, that's bad. You can do better than that. I swear it can do better than that. Let's see. For some reason, it can read the little writing on these pins. So sometimes that makes it a lot better. So in part C, they're asking for E total. So as I said, E squared is equal to P squared C squared plus M squared C to the fourth is one version, but you can also say that E is equal to gamma MC squared. And it also turns out the kinetic energy, which you might just call K, is gamma minus 1 times MC squared. So those are two versions you can do. When you found gamma, by the way, gamma is equal to 1 over the square root of 1 minus beta squared. I do 1 over the square root 1 minus beta. Beta is 0.999. And if I remember correctly, this was actually, never mind, I won't try to do that. I actually did a derivation for however many nines you have here, telling you exactly what beta has to be. But anyways, I didn't, I don't want to use my memory because I'm liable to screw up. So I'll do, and this is squared, forgot to write the squared there. So I'm going to do 1 minus 0.999 squared. I'll take the square root of that. Whoa. Square root, whoa, did the wrong thing again. I want, now the answer. I kept trying to square it by mistake. And now I got to do 1 divided by that. And I get 22.366. So the gamma factor is 22.366. If you wanted the total energy, then you just say, okay, E is equal to 22.366. And I obviously carried 2 extra digits there times MC squared. But MC squared is 106 MeV per C squared times C squared, which you can see now, duh, if I write it as MeV per C squared, the C squareds just cancel out. And I'm going to get 22.36 times 106. And I get 2.371 times 10 to the third MeV. Of course, 10 to the third MeV is a GeV. So you should get about, they said 2 sig figs, I think. So it's 2.4 GeV, roughly. Ain't that the right answer that they gave you?
Give me 1 second to write down what you wrote down. Can you move your pen for a second? Thank you.
Yeah.
For GeV, and the answer was 2.37. So it was to 3 sig figs.
All right, so exactly what I got. That's good. For some reason I was thinking it was 2 sig figs, but yeah. Does that make sense?
Yeah, that makes more sense. I have one more question. It kind of so let's see. Let me share my screen again. It's for part F on the same kind of like area.
Okay.
And so I'm assuming like what I did for like A and B, I just kind of like switched the values. I had the same equation, but like switched the values for muons and pions.
Mm-hmm.
I'm assuming I could do the same thing here. So I just kind of wanted to know like how to do this for pions.
Okay, so your pion probably has a different half-life, or excuse me, a different lifetime. So what you're going to do is you're going to take that particle traveling at whatever speed they said, maybe 99.9% of the speed of light or whatever. Does part E give you that?
Part E, it says, how far would the muon travel before it decayed if there were no time dilation? And that's
gotcha.
This.
So you just did 2.2 times 10 to the negative 6 and multiplied that by gamma. Or excuse me, not even by gamma because they didn't want you to do that. Just multiply that by the velocity. And that gave you 659 meters. Now let's consider the effects of time dilation. How far would the pion actually travel before decaying? So again, this is just a case of doing velocity times a lifetime. If you wanted to actually figure out how far it can go, then you're going to have to do the dilated lifetime. So you do gamma times the life of the pion, and then multiply that by V, which is 0.99. But in that case, you actually have to use meters per second as opposed to, just 0.99 and stuff. Does that make any sense?
Yeah, that makes sense. I was kind of confused as to like how to go about it because I think I did do like the lifetime times gamma,
Mm-hmm.
and I probably accidentally left out v. So I had like a different answer, and I was kind of frustrated. So I just requested these answers.
Yeah, watch your units. If you do something like that, the units would probably come out without a meter, so that would help you. So if you keep your units on your numbers when you're doing the calculations, that'd probably keep you from making that mistake. But yeah, in this case, you're just going to multiply the velocity times the dilated life. So gamma times the life of the pion times the velocity in meters per second should give you how far it will travel.
Okay, thank you.
Okay, and yeah, check out those special relativity examples that I did on my YouTube channel. They're easily, looked up. You can just do a search for special relativity.
Okay, thank you. Have a
No
good one.
problem. You too. Lauren, you want to post your question now? And anybody else after that?
Yes. Just kind of pull it up. I was confused on this part for both questions.
Okay. Reference frame S prime moves at speed 0.93 c in the positive x direction with respect to the reference frame S. The origin of S and S prime overlap at t equals t prime equals 0, and objects are stationary in S prime position at x prime equals 120 meters. What is the position of the object in S when the clock in S reads 1.5 microseconds according to Galilean transformation equations? And okay, so what you're doing here is you're assuming that a coordinate system is moving at 0.93 c. They want to know x prime is equal to 120 meters. V is equal to 0.93 c. And they want to know what the position of the object in S when the clock in S prime reads 1.5 microseconds. And this is Galilean. Okay, let's kill that for a second, and I should be able to help you with this. So what we're doing is we're imagining a frame X, and in this case you could say Y, and it's moving at 0.93 c, and this is actually X prime and Y prime. And then there's X and Y, which is actually sitting still. So if you take this one particular point here, which is X prime, then obviously X prime is this distance. And then X, of course, is this distance. So what you see from Galilean relativity is X is equal to X prime plus VT. Okay, that's what Galilean relativity would say. And there's no sense in putting mark on a prime on the T, because there's no difference in time in Galilean relativity.
What about gamma factor?
But we're talking Galilean relativity, so there is no gamma factor. That's sort of the first point of part A. Part B, they're probably going to want you to do the relativistic one, which becomes X is equal to gamma X prime plus VT prime. But by starting off with Galilean, you can sort of see the difference between relativity and not. So they're going to say X is equal to 120 meters plus 0.93 times 299,792,458 meters per second. Obviously, you can just do 3 times 10 to the 8th meters per second if you want. And then times time, which would be 1.5 microseconds. So it's 1.5 times 10 to the negative 6 seconds. Okay, so let's try that out. And I'll do 120 plus 0.93 times 299,792,458 times 1.5 e to the negative 6. And I get 538.2 meters.
So the first equation, x equals x prime plus vt, is the Galilean. And the one with the gamma factor is the
It's the Lorentz or relativity one. Yeah. Lorentz made it up, but Einstein made sense of it. So you could call it the Einstein or the Lorentz transformations, but it really is called the Lorentz transformations.
Because I was really confused on the difference between them. Because they both look the same.
Well,
But
yeah, I mean, but the
in the
difference
book,
is, go ahead.
in the book, I was just thrown off about it because I think I saw, because when I was looking at it, I saw the use of a gamma factor in the Galilean. So I didn't know which one to really pick.
Gotcha. So yeah, the Galileans just before we knew the speed of light is a constant, and before we understood that time is different in different frames. So Galilean relativity is x equals x prime plus vt, y equals y prime, z equals z prime, and t equals t prime. When we go into Lorentz, we get this for the first one. Then we get y prime or y equals y prime, z equals z prime. But then t becomes really confusing because t equals gamma parentheses t prime plus vx over c squared, where it's actually vx prime over c squared. So that's the difference in the Lorentz versus the Galilean relativity.
Okay.
No, that's Texas is next Sunday.
Have you tried that answer that I just gave you?
Yeah.
Or did you already?
I ran out of attempts for that one, and yeah, that's right.
Oh, that's the one they give you. Okay, gotcha.
But I didn't run out of attempts for the next one though.
Gotcha.
But
So put that one up and let's see what we can do with that.
it looks more. It's a lot more simple now that I figure out the difference between those two.
Yeah, between
equations.
Galilean and Lorentzian.
Yeah. See this in the next one.
What is the position of the object in S? Oh yeah, they got a 3.9 instead of a 3.8 because I used all the digits of that. If I'd used 3.00 times 10 to the 8th, I'm certain it would have came with 539. What is the position of the object in S when the clock in S reads 1.5 microseconds according to Lorentz transformations? So yeah, in this case, you didn't use all your attempts, but in this case, you're going to say X is equal to your gamma factor, which would be 1 over the square root of 1 minus 0.93 squared times x prime plus vt prime. So in this case, the gamma is 1 divided by square root of 1 minus 0.93 squared, and I get 7.402. So I carried more digits than they gave us, of course. And actually, you only gave us 2, so it's that 7.402 is your gamma factor, and then x prime is 120 meters, and then again we'll say 0.93 times 3 times 10 to the 8th, and then I multiply that, of course, by 1.5 times 10 to the negative 6 seconds. So let's see what we get when I do that. I'll do 120 plus 0.93 times 3 exponent 8 times 1.5 exponent negative 6. So I got 538.5, which is again like that 539. But now I have to multiply that by 7.38 or 7.402. And that gives me basically 3.986 times 10 to the third meters, which you probably just going to call 4 times 10 to the third or 4,000.
Can you move it down a little bit?
Yes.
Okay.
So basically, it's traveled, a considerable distance over a time of 1.5 microseconds. So obviously traveled hundreds of meters. Then it already had 120 meters added to it. And then, of course, the gamma factor gives it an even higher number. Have you tried this answer on? You might call it 4.0 because I think it wants it to 2 sig figs. You call it 4.0 times 10 to the third meters.
I'm about to try it. I was just writing it down real quick.
Okay.
Said 3.99.
Yeah. Times 10 to the third.
To the third.
Mm-hmm.
I think I used too many sig figs because it didn't work. I think I used too many sig figs. Point oh. No, it's not working. Now I only got one attempt left.
Show me that question again. And let me know when it's up. I'm looking at something else on a different screen right now.
Oh, it's up.
It's up. Okay. Okay, there it is. So what is the position of the object in S when the clock S reads 1.5 microseconds according to the transformation equations? Okay, so I'm looking at that. Let me move this to the side a second, and let me go back and look at what I was looking at. Is this homework part 2 or is this homework part 1?
Part 1.
Okay. Thirty-six. There it is. And what's this problem called? It has some weird name like
It's problem 36.24.
oh, okay, gotcha. I'm opening it up so I can see the whole thing at once on my side. all looks good. We're doing part B, are we?
Yes.
Okay. Oh, duh. So, okay, here's the problem that we forgot to do. And that's just a bonehead mistake on my behalf. So, let me see, how's the best way to do it? Okay, so first off, everything I did was right except for this. I used, and I should have done that before. Let me, okay, yeah, you're looking at this. I didn't know if you saw the screen. So this was right. The problem is, notice I did make a point that t was 1.5. I just randomly, accidentally used that for t prime. That is not t prime. Remember, the Lorentz transformations are x is equal to gamma x plus vt with primes there. Y is equal to y prime. Z is equal to z prime. And then here's the weird part. T is equal to gamma t prime plus vx over c squared. So I have, and actually this is x prime. I have to actually compute what t is to use, what t prime is to use it in here. So in that case, I actually have to go back and say, okay, well, t prime is going to be, in fact, gamma times t minus vx over c squared. So I can put the 7.402 there. I can do the 1.5 times 10 to the minus 6 seconds there. I can do minus the 0.93 for the velocity, and then the 120 meters, and then the 0.93 is actually supposed to be times c, but I already have over c squared. So one of those is actually going to cancel out like this. And now I can get the actual t prime that I'm going to put in here. So the problem was I just misread that. I misread that. That was actually supposed to be t prime, which I'm getting now. So let's do this. I'll do 1.5 e to the negative 6. And now I'm going to subtract from that 0.93 times 120. Again, it's times c because it's v times x, and x is 0.93 times c, but one of those c's cancel out, so I'm just going to divide that by 3 exponent 8. The stuff in parentheses becomes 1.43. Times 10 to the negative 6, and then I multiply that by 7.402. And I get 10.64 times 10 to the negative 6 seconds. So that's what I should have put in there instead of that. Now let's try that. So I'm going to multiply this 10.64 times 10 to the negative 6 seconds. I'm going to multiply that by 3 exponent 8. I'm going to multiply that by 0.93. And then I'm going to add to it 120 meters. Okay, so now I get that x is equal to 7.402.
So you saw for t prime and then plug into the original equation.
Exactly.
the x.
Yeah, so now I'm doing that. I'm saying plugging it back into this now, and this is 0.93 times 3.00 times 10 to the 8th meters per second times 10.64 times 10 to the negative 6 seconds. So I'm doing all of that. What I got for inside of these parentheses, by the way, was 3.090 times 10 to the third. And now I'm going to multiply that by 7.402. And that gives me 22.90 times 10 to the third meters. And hold on, let me check that real quick. That seems way off. So we were told that T was 1.5 seconds, but that's the one that it's moving with respect to. So we actually got to get a bigger time. Oh, there you go. I don't think that's right either then. Well, let me, hey, let me get back with you on this one. Is there another problem you had?
That
Yeah.
same question that he had, because I couldn't figure out what is a pion.
Yeah, a pion is just another
pion.
particle.
I mean,
yeah. It's supposed to start pi like the word, like the Greek letter pi. So that's why I call it pion. The other one was muon. But yeah, it's just a matter of taking those masses, those energies, using those expressions. This one, like I said, it's bothered me a little bit. Don't answer that part B. I'll send you an email after I work it out. This looked okay, but I think I might have made a mistake in that I was trying to get the time. But notice I got a time in the frame that the object is sitting still that was actually less than the time that I got for the frame that's seeing it move by. And I thought that's right, but now I'm doubting myself. So I'll have to figure out what's going on with that one. But anyways, I will